Sorry for the altercation. My video was cut the last time, so I will continue. Let me pause this. So as I was saying, this checks the initial state. This is the initial state. If it's off and this is the current state is on, that's only when it will be triggered. So it avoids double triggering. That is in a situation where it was triggered the first time and it gets triggered again. So this is actually the interrupt that marks the start of transmission. Now this is a very crucial part of this whole circuit, this particular area. This is where the output is generated. So this is the output after the whole bpsk applied on it. This is the output and this is how it's being generated. So first of all, I will wait. Okay, it's okay. So it's going okay. First of all, this bit here is the output enable. I will still show you how it was generated. So this is what triggers this. So this bit here is the output enable. So if it's equal to 0, that means this multiplexer is off. That means it's going to reset. So if the output enable is 0, reset the output. If not, get this input here. This input was right shifted using this out div. This out div bit comes from the PLC. Is an offset, is constant, so it is a constant you can set. It's more like a precision, used for making precision. So remember I told you earlier that the right shift means division. So whatever value is here means whatever is the output, you divide it by a constant. So it's used to gauge the resolution of the bit. So is where you can set it. If you set it to 0, that means there won't be any shift. So it depends on the arrangement within the PLC sub-circuit. So then here, what is happening here is this is the phase. This input here is the phase. So this phase here represents ones and zeros, which we want to transmit. But as it is now, we won't be sending them out as ones and zeros. We'll be sending them based on what sequence are they in. Look closely. It says if is equal to 0, that is 0 here. If the phase is equal to, I'm going to show you where this phase was generated. But it says if the phase equal to 0, this will be triggered and is going to take the sequence directly. This is coming from the sequence, as you can see. Else, if it's equal to 1, subtract 254 from it and give us the output here. So this is where the subtraction came. FE in binary is 254. So let me explain what using this. Just as I told you, once the sequence counter is going, so it's going clocking 127, 166, 202, 230, 248, 254, 230, and so on and so forth. So if assuming it's going down and it gets a 0, it takes the actual value 166. If it gets a 0, 202. But if peradventure it gets to somewhere at this 202 and it gets a 1, so you're now going to do 254 minus 202, which is going to give us what? 52. So this is where the phase shifting occurs. This is how the phase shift. So assuming it was going from 0 and it came to 24 and then it gets a 1, then you do 254 minus 24, then you are going to end up with 230. So instead of going the normal way, at a point maybe easier, it will now start going like this, or maybe instead of going like this, it will now start going down again like this. So this is actually how the phase shift how is phase shifted using this sequencer. This is actually what I describe as the sequencer, and that is what is actually fed from you can see the part is actually fed from up here down to, sorry, let me highlight it more, from here. Once it's coming from hey, what the fuck. So once it's coming, oh, the problem. Sorry. So once it's coming from here, it comes out through here and continues its journey down until it gets to this place. So this is where it either goes directly or it's being subtracted depending on the phase. So this is the phase here. So if the phase is 0, it takes it directly, else if it's 1, it does the subtraction and brings out the output here. So I'll now show you again. So this is the output. So I'll now show you how this phase is being generated. First of all, I will tell you a little about the packet. So this is what the transmission packet looks like. Sorry, let's see. Oh, let me pause it. This is what the transmission packet looks like. So it consists of a 64-bit magic pattern. It's called a magic pattern. You see what it looks like. Then a 32-bit by 16 data output. Then a 32-bit checksum. So this is what is going to be modulated and transmitted, making it a total of 608 bits. So 64 bits magic pattern, 32 bits data, and 32 by 16 bits data, and 32 bits checksum. So I'm going to show you the magic pattern is a constant actually. We will generate the checksum and I'll show you how this data came about. The 32 by 16 bit data actually came from our PLC circuit. Remember, the data to be sent comes from the bus write data. When we were talking about the PLC circuit, the bus write data, I showed you how it was spread among the 32 bits by 16 blocks. So that is the data that is going to be sent here also. Then the checksum. So we are back here. So let me first of all show you how the checksum. This is the checksum here. This is the checksum. My laptop is not, the buttons are not working well. So let me show you how this checksum was generated. Already the data output is here already. These are the data from the PLC subcircuit. They are here already, but let me open the checksum subcircuit and show you something in the checksum. So this is basically what the checksum does. It takes all the data bits and XOR them. So it XOR all the 32 by 16 bits of data and XOR them, and that is how you get your checksum. It's going to be received at the receiver. So whenever the receiver receives all these packets, it's going to take the 32 by 16 bits which it received, and then I'm going